Okay, good morning, everyone. Good morning, Professor Nakajima. Can you hear my voice?
I can hear you. Good morning.
Okay, good morning. Nice to meet you. And
You
I
too.
think the class will start in 2 minutes. Okay,
Okay.
so we are still waiting for the students to join. Okay,
Okay.
thank you. So, Vera, can you hear our voice?
Yes, we can hear your voice.
Okay,
Thank you.
Nine o'clock. And first of all, let me introduce myself. Okay, my name is Monglin Chai, and I will be hosting this morning's class. And we are happy to have two professors joining with us today. And in the afternoon, I will go to the classroom to join your lab course, and also to evaluate your presentation and the progress of your project. Okay, and let's start uh, with today's first part of the today's lecture. And it's my honor to introduce Professor Nakajima. He is currently the professor in the School of Materials and Chemical Technology, Tokyo Institute of Technology. And his research mainly focus on the nanomechanics of polymers. Okay, and today he would like to share with us the topic related to the mechanics of polymers. Okay, so please join me to welcome Professor Nakajima. So, Professor Nakajima, you can upload uh,
Okay.
your
Yeah.
slide. Okay, thank you.
Okay. Thank you very much, Professor Tai, for introducing me. And okay, let's say, 大家好，我叫中岛健，我是东京工业大学的教授。Okay. And so now I'm sharing my slide. Just a moment. So now, are you looking at this one? Oh,
Yes, we
just a
can
moment.
see it clearly.
Something
Okay.
wrong is happening. Okay, I hope now you are looking at this slide. And I will just a moment. First of all, I show you the today's the assignment for you. And I'm not sure that you need to submit the assignment for my lecture or not, but if necessary, then please submit your report on my lecture. And the content is just what did you hear during listening my lecture, and using 500 words or something like that. So it's quite easy, but please listen carefully, okay? So now I will make it in the first page, okay, and making it. So now I hope you are looking at in a full screen mode, right? It,
Yes, yes,
and it is moved to a second page, right?
yes, that's right.
Okay, so then moving back. So now the system is working very well. So okay, once again, let's start my lecture. It's on yeah, title is Nanomechanics of Polymer and Lava, but because I heard that many of the students there is the major is in the kind of mechanics or robotics or something like that related to the engineering. So in your daily life, you may use polymers or rubber materials as one of the components of the systems. So I'm not going into the detail of the very deep part of the material science, but very briefly introduce what is polymer and what is rubber and what kind of properties can be expected for such materials or something like that. And also together with me, as a second lecture for today, the Professor Kuboyama also will give a presentation on polymeric material. So I think he will talk about the something like that, the polymer blending or alloy or something like that. So I this time just focusing on rubber material, and I think many of you know about the rubber because you may use the rubber material as a component, as I mentioned. But I this time want to say to you that why rubber show the rubber elasticity and what is the origin of such the mechanical properties. That is what I want to deliver to you. Okay. So, so here is my face, and also my name is Nakajima. In Chinese, Chondao. And but because I'm a material scientist, especially on rubber, so please just call me Dr. Rubber or something like that. Okay. And also during my talk, I will call some of the big scientists like Jules Feynman or Einstein during my talk, and which you may know some of them and may not know some of them, but I will introduce these guys during my talk. Okay. So first, let's start with the so-called Gauss-Joule effect. And the Joule is a famous the old professor on thermodynamics. Thermodynamics. Okay. And so first, I stop sharing this. Just a moment. Stop sharing, and now you are looking at my face, and also maybe in your hand you have a rubber band. So let's start the simple experiment together, okay? If you have a rubber band. If not the case, please do it later on. So here is a rubber band, and then, oh, now you are distributing. Okay, then I will wait for a while. Okay, thank you for maybe better, or thank you very much for helping me. Okay, now you have a rubber band in your hand. Then first, just put the rubber band here or on your lip to measure the temperature of this rubber band. Okay. Of course, it should be the room temperature. Then please slowly elongate it to the maximum. And once again, measure the temperature. Okay. No change. Then after that, please look at me. So suddenly get it back to the original length and measure it. I think you felt something become different from the beginning. Temperature decreased or increased. Okay, maybe if you write the decrease. And once again, then now quickly pull and once again measure it. Then temperature increases. You felt similarly to me. I hope so. This is so-called Gauss-Joule effect. Okay, now I once again share my slide. Oh, where is it? Just a moment. Oh yes. No, no, no. I once again share my slide. Okay. Yes, and make it the full screen mode. Okay, so the simple experiment was over, and you felt when we pull the rubber band quickly, then the temperature of the rubber band become uh, warmer, hotter, I guess. And this is what we we experienced. Okay, so the Professor Zhu is the old the scientist in 19th century, and he found this phenomenon. Originally, this was found by Professor Goff, but Professor Zhu explained this phenomena by using thermodynamics. Okay, I think. No, no, sorry. This was also discussed by Professor Feynman. You may know the Professor Feynman as the author of the very famous the textbook on the physics, and in his the textbook, you can find this figure, and here they are the old rubber band stretched on this type of shape. Then this portion is heated up by something, and then this start to rotate. And if you are interested in this, please refer to his textbook. Or you can also find it in the website, because now his textbook is freely available online. Okay. Then I also did the similar measurement by my. This is not mine, but yeah, here this portion is heated, and then it start to rotate in like in this the movie. Yeah, so I think you may not know about this type of phenomena, but apart from the lava, you also have heard about the story of cloud formation. Actually, in Japan, we have learned this phenomena when we were in the junior high school students. Then, as is in this cartoon picture, the why cloud is formed. This is because when we have some kind of pressure differences, then some the water vapor containing air is raised up. Then because of pressure decrease, then the volume expands. Then because of when the volume expands, then this air temperature get decreased. And then that's the reason why the water vapor is now turned into water droplet. That the reason why the cloud is formed. And similar the things can be performed in the room, like in this cartoon. And this is actually obtainable from the textbook for the junior high school student. And similar, actually, sorry, just a moment. So this is the movie for that. Okay, so now here is it contains so many water vapor in it. And then first we put the air with the pressurized air in it. Just a moment, maybe it's too long. And then giving compression. Then suddenly the cap of the bottle gone up due to a high pressure. Wait, and then it's currently transparent inside the bottle. But okay, yeah, now because the sudden expansion of the air, and then the air temperature decreased, and then cloud was formed. Okay, so now we have looked at two different phenomena. One is the Gauss-Jule effect. The other one is the gold cloud formation. And the important point is that both phenomena occurs on a sudden change of the volume. When you stretch the rubber band, then of course the rubber band, actually volume doesn't change so much, but okay, but anyway, stretched. And the case of a cloud formation, adiabatic expansion is occurring. But the result is opposite. Case of a Gauss-Jule effect, the rubber band was heated. But in the case of air, it was cooled. Why this difference was observed? Unfortunately, the thermodynamics cannot explain this difference. Then we need to move to the higher level discussions which can be made by so-called statistical mechanics. I'm not sure you learn the statistical mechanics in your department. Especially, I heard the Tokyo Tech student is also there, but you are from department engineering, then you may learn thermodynamics when you are the first grade of the Tokyo Tech student, but may not learn about, sorry, just a moment, may not learn about the statistical mechanics, but very briefly, I will explain this portion to you. So before going into the detail of statistical mechanics, we just remind you about the kinetic theory of gases. I think in this case, many of you have learned this when you are in a high school student. Okay, and this actually connect the nanoscale object and macroscopic properties. I mean that the gas molecules and air. Okay, so now looking at this one. So of course, these gas molecule is too small to look at, but this guy, the Professor Boltzmann, use his imagination what is happening inside air, and these small gas molecules moving around very quickly, very randomly, random direction, and the random the velocities, and this resulting in the everything observed in the air. For example, the pressure or something like that. What you have learned when you was the high school student. Okay. Then I hope you also know about this equipartition theorem. So each of the molecule has energy, and energy can be written in this formula. This is what I'm sure you know that the m is the mass and the v is velocity. And if you take an average of this quantity for all of the gas molecules, then you can make this value into this formula, Kb and T. And T is actually the absolute temperature, and Kb is so-called the Boltzmann constant. And you may know that the V for the gas molecule is about several hundred micrometer meter per sec, very fast. So they are so, what to say, cheerful, the gas molecules. So okay. Then this portion is something bit difficult and need some explanation, but please, because of the time limitation, I cannot go to the detail of that. But when you have learned the thermodynamics, you heard about some technical term, entropy. And this entropy is actually used in some equations of the thermodynamics. But I'm quite sure that the many students do not really understand what the entropy means. And actually, the meaning of entropy in thermodynamics is not so easy, actually. But if you go to the statistical mechanics, then entropy S has a more practical meaning and correlated with the quantity of W. And what is W? W is the number of the microscope, the states, which I will more detail explain later on. But anyway, summary, thermodynamics treat the material macroscopically. So, for example, taking the air as an example, we just treat the air volume, temperature, pressure, or something like that only, just visible by ourselves. But the case of the statistical physics, we go into the deep nano size or less, and talking about the component of the air, gas molecules, and then that of course we are treating the same phenomena, so they should have some correlation to each other, and which is this Boltzmann's formula. S is equals to KB multiplied by log W, and W is a number of the microstates. What is a microstate? Oh, just a moment. Sorry, I made a mistake. Oh, just a moment. I made a mistake. Okay. I hope you are still looking at my slide. If not the case, let me know. Okay. Okay, just forget about that. And so now I'm talking about the definition of a microstate using this very simple example. So assume that this circle is a gas molecules and he's really quickly moving inside a room. And if we divide this room into the small cells with a similar size of the size of these molecules, then for this molecule, this room is divided into 14 multiplied by 9, and as a result, 126 small cells. And because this gas molecules travels inside this room very quickly, and if you are looking at, if you just look at these molecules as a snapshot, for example, then you can find this gas molecule somewhere. Next time, somewhere else, somewhere. And because that you will see with this gas molecule existing in one of this cell is equal probability. So which means the microstate means now this is one microstate. The another microstate is you find the molecule not here but here. And so different the microstate. How many different microstates exist? Yes, of course, this is 126. Okay. Then, if you take a log for this value and multiply by k, and which correspond to the value of entropy. This is the definition of entropy in statistical mechanics. Now, make this room double. Then what's going to happen? Yes, of course, the number of the microstates also become double. Then, due to this, entropy also become larger than that. in this way. So, due to this, if you expand the available room for gas molecule, then which resulting in the increase of entropy. So this is a case for gas molecules. Okay. Please remind that we are now want to differentiate the case of air and the case of rubber. Okay. So now let's start. Yeah, you can just forget about this. This is a more exact formula for the entropy. So now let's get back to the story of the polymers, especially for the rubbers. Polymer is a chain-like molecule. You may know because at least in Japan all the student, the high school student learn polymer. The polymer is like this. It's chain-like molecules, and for example, this is a polyisoprene unit. So we have a small molecules like this one, which interconnect to each other to form a long chain-like structures. And this now become a single molecule for the polymer. So it already has contains so many atoms, and the length also go to 100 nanometer or so. So this difference, so compared to small gas molecules, these high molecular weight materials exhibit some different property, which I will discuss from now on. So first, please have a look at this movie. So this is a computer simulation movie for the single polymer chain. It's actually moving quite rapidly, like and quite randomly. So changing the shape time by time. And this time scale is actually picosecond or nanosecond level. And I want to remind here that because each small the component of polymer chain is the size of them as quite similar with the gas molecules. And as I mentioned, they have the case of a gas molecule, the velocity for each gas molecule was 100 meter per sec. And this energy is also kept in case of these polymer chains. So they basically have a velocity with the same value. But due to the interconnected situation, they cannot just moving away, but just the moving quickly inside this the cell. Okay? And this very random, very quick motion is the key to understand why polymer chain shrink small. By the way, I'm just using a few minutes. Let's get back to junior high school. Actually, this is I got this. Sorry, this is written in Japanese, but extracted from entrance exam for the junior high school, and this junior high school, Taisei. Oh, sorry, Japanese, and the Japanese people knows about that. Most famous junior high school, with known as a high level junior high school. And then for this entrance exam, I will not go into the detail of that, but please have a look at this portion. And then the question is, first, the simple question is that starting from this point A and moving to point B, how many different shortest paths exist? So from A here, so moving this way or this way or something like that, how many different pathways exist? And if you are the elementary school student, you know how to solve this. Yes, of course, from here to here, only one route. From here to here, only one route. So to come here, there will be a two route, this route and this route. But and also similarly, to go to the point B, there will be a 10 different routes. And if you are the junior high or high school student, you have learned how to calculate it because the shortest route can be expressed in this way. For example, first up and turn go right and right and up and right. This way, then the different route is just the different ordering of these the arrows. So the number of the different route can be calculated in the combination 5, 2, and it equals to 10. This one. The difficulty of this entrance exam is the Japanese people can read it, but in this the rule, he allows coming back once to the left. Then how many different shortest route is? Then this the problem become really difficult. Just putting this new rule, turn go to left once. But we will not go into the detail of that. But I will get back to just a moment. Get back here. So now get back to the polymer chain. We want to count how many different shape exist for the single polymer chain. Then first we stop the fix this end here and another end here, and the other the small component can be located anywhere, but asking them to form chain-like structures. Then this this figure shows the case for the both end distance is 8, and the contour length is the total length of this the root is 18. Then how many different paths exist? This problem is not easy to be solved. Need maybe computer calculation. So I will not go to the in a calculation manner, but you can imagine there are so many different paths. Okay, but most simplest case exists. This is this. So now the distance between two ends and contour length is same. Then we can definitely say the number of their possible route is only one, which means the microstate is only one. Then entropy is the log of W, so equals to 0. Compared to this, in this case, because the microstate means when the distance between two ends is 8, how many different microstates exist? Actually, so many. And if the distance between two ends is 7, 6, 5, decreasing, then you may imagine the number of the microstates increase. And oppositely, if the distance between two ends increases 8, 9, 10, blah, 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 and until 18, the 18 is a maximum number for this case, then W becoming 0, as a result, entropy becoming 0. So, case of a polymer chain, if you elongate it, the entropy decreases. That's the difference between two phenomena: Gauss-Jule effect, cloud formation, the polymer chain molecules, gas molecules. Case of gas molecules, once again, by increasing the volume, entropy increased. But the case of a single polymer chain stretch, then entropy decreases. This difference actually reflects is reflected to the macroscopic thermodynamic phenomena. So let's summarize in this way. If polymer chain is stretched, then because that, as I mentioned, these guys, these kids, want to move quickly, like in the gas molecules. But if stretched, then they have no freedom, resulting in a W equal 1, entropy is minimum. And then, because that entropy naturally goes to the change in an increasing manner. So if this restriction is disappear, then polymer chain get to smaller shape. Due to by this the S increases. So this is a natural trend. The polymer chain, its shape, try to get to smaller as much as possible. That's the reason why the rubber get to shrink when you release the force. So we call the elasticity for rubber as rubber elasticity, but its original mechanism is coming from the entropic elasticity of a single polymer chain. Okay, and starting from this idea, Gaff-Joule effect can be calculated in this manner. And I will not go into the detail of that, but the delta T temperature difference is of course correlated with how much you elongated the rubber band. But most important quantity is here. S is here. So the change in S due to L can be correlated with this temperature change. This is what first I wanted to deliver to you for this my lecture. And okay, this is the very famous Japanese TV program, so-called Chiko-chan. Some of you may know that, but in this TV program, the Chiko-chan also put the same question: why does the lava stretch and shrink? And she said that because lava looks like very quite similar to water. Yeah, actually I mentioned that, but yeah. So I appear here and I discuss this. Yeah, forget. Okay, and also I use this lava or this type of things to explain some detail, but it was too difficult for the people. So I made interesting the virtual experiment using a human being. Just a moment. Just a moment. I made a mistake. So I asked these guys to follow this phenomena, but I didn't tell them how to move. But I just asked them to freely move. Then, because they want to do something, what they want to do, and then the shrinked shape is naturally formed. But once stretched, sorry, I made a mistake. Yeah. If it was stretched, of course, they lost the freedom. And once released, then they get back to the original shrinked form. This was what TV program tells us. Yeah. Okay. And the similar situation can be, of course, reproduced by computer simulation. When we start from this elongated shape, this is a model for the single polymer chain. And now the distance from the both end is about 30. Then for this computer simulation, these small component just move if possible. For example, this portion cannot move because these other the point located here and no way to move. So at the beginning, only this guy can move this way or this way or this way randomly. And I expose all of the components just move randomly if possible in computer simulation. Then what's gonna happen? Oh, why it doesn't move? Oh yes, start to move. So first these the both ends start to move, but now the many of the components start have some freedom. Then finally it get in a shrinked shape. The size also becomes from 30 to smaller value, and actually this small value should become root of 30. So like 6 or something, 5 to 6. So it actually got coming here. Okay. So this is quite natural. The elongated, the component get to small shape. So this is a natural trend. So I show you several examples why polymer chain have a shrinked form naturally, and once elongated, they feel force. And this is the origin of rubber elasticity. And I used the virtual experiment by using human being and also computer simulation. But I think you still feel that is this really correct or not? Is this chain-like molecule really want to shrink by themselves? Yes, I also have a same question. So I wanted to do this experiment, a real experiment for using a single polymer chain. So to do so, I used atomic force microscopy, AFM. I'm the my expertise is actually this the interesting microscopy, which was first developed by these three guys, especially Professor Binich, Dr. Binich, and Professor Kuwait in Stanford University, and these two guys are from the IBM. And this microscope has gained the Kavli Prize in 2016, and different from the conventional microscopies. For example, you may know the optical microscopy, or some of you may also know the electron microscopy, but any of them use a kind of lens to magnify the small object to larger scale. But this AFM has a different principle. So as is written here, we use this very sharp tiny probe, and this place on the sample surface, and this tip is scanned over the sample surface to trace the shape of the sample surface and reproduce the image. And because you know that this tip top is coming and made from the single atom, ideally, then this tip probe can trace the atomic scale evenness. So to reproduce the atomic scale imaging. That's the very simple explanation of this AFM. And the people actually use this AFM to visualize their molecules. For example, this case, this is a structure for this the organic molecule, and this is a real image of these molecules. And yeah, so now you can look at inside the small molecules. And another example, this use of this AFM is by my friend Keiji Tanaka, who did the visualization of a single polymer chain solved on the flat substrate, silicon, something like that. So now we know polymer chains really chain-like structures with different shapes. But in this case, because the polymer chain is strongly adhere on the substrate, they doesn't move. They don't move. So my research was a bit different. So I place polymer chain in a liquid medium, and one end is fixed on the substrate, and the other end is floating in this way. And then we bring AFM probe on it and pick one end and stretch it and measure the force. And this is cartoon movie, but we can do this using a realistic AFM instrument, and this is one of the results. So the lateral axis is the extension length of the single polymer chain. Originally, its shape is like 5 nanometer or so, but because it is the shrinked formula, then by stretching this, then you can thread to the maximum, and total length of the single polymer chain is like 200 nanometer. So 0.2 micrometer, very small. And the fourth level is also very, very small. It's piconewton level, 10 to minus 12. So you may not be able to imagine how small is it. But this is for the single polymer chain. And more importantly, as you can see at the beginning, you have the kind of the proportional relationship between the extension length and the force. So I mean that the straight line at the beginning was observed. So this is entropic elasticity experimentally observed. And here is several different models written. I will not go into the detail of that, but there are several models by the statistical mechanics. For example, the freely jointed chain or worm-like chain models, or something like that, and which can be compared with experimental results. So this, we are now in such a level. So we have evidence that the single polymer chain has entropy elasticity, no problem. So a theoretical treatment was true. And because rubber, the rubber band is made from the so many chain molecules in it. And that's the reason why rubber has elasticity. And I want to introduce one very famous Japanese professor, Professor Kubo, who is one of the founder of statistical mechanics in the early 20th century. And he wrote this textbook. Sorry, this is Japanese, but this means rubber elasticity. When he was 25 years old, he was already the professor of University of Tokyo and wrote this textbook before writing more deep the textbook on the statistical mechanics. So the Professor Kubo has first interested in this interesting rubber material and wrote a book. So for me, I'm a material scientist of especially on the rubber material. So I'm quite happy that this Japanese professor, famous professor, have interested in this the same material with my interest. Okay. Anyway, Then, because of time limitation, I cannot go into the detail of lava elasticity, which is made from a single chain interconnected to each other with the cross-linking point. I hope the Chinese people also can, and the Taiwanese people can also read this Chinese character. So the cross-linking point, and then due to this cross-linking point, then if you pull this the rubber sheet, for example, then the inside this rubber sheet, the polymer chain is also elongated. Then due to entropic elasticity, the rubber themselves, the holes the rubber sheet also feel the restoring force. That's the rubber elasticity. And this is just the computer simulation result for that. So polymer chain. Oh, this is very important. Sorry. So if I ask someone that the is lava is in a solid state or a liquid state, then many percentage of people says, oh, it's of course the solid. Yeah, because you know that the shape doesn't change. But if you look into the very small scale and which are now the molecules now start to visible, then like in this the simulation, the chains, each component, small component, for the polymer single polymer chain, moving around. So macroscopically, the lava would be the solid, but microscopically, lava is in a liquid state. Please remember, this is very important point. Different from the crystalline material, like that any type of metals or yeah, for example, ceramics. For example, this is the first of all, the metals or any other kind of inorganic the crystals, the atoms doesn't change its position, just vibrating, centralized, vibrate with a small amplitude. But in case of a ceramic material with amorphous state, and then although the long range order doesn't exist, but each atom doesn't move. So they are in a solid state microscopically. But in case of lava, the each atom change their position time by time, like in a liquid situation. And that's the reason why the lava has the very special elasticity. Okay, so may I continue? Or take some rest? We still have 30 minutes or so. Okay, let's take a 2 minutes break to refresh. That your position. Let's restart. So, may I start? Okay, I hope.
Yes, yes,
Okay,
no
yes.
problem.
So, from now on, up to now, I have discussed the kind of molecular level, the mechanisms of lava elasticity using computer simulation or something else, and also comparing with the gas molecules of why polymer chain is totally different, has a totally different property with the small gas molecules because of these chain-like structures. But from now on, we will start to discuss or something a macroscopic property of the lava materials. So first, this page shows the relationship between sorry, in Japanese, strain and stress relationship of a single polymer chain. No, no, no. Lava band. So very different from the other material. Lava has a very special property. Can be elongated very much, like 100%, 200%, 300%. Never be achieved by other materials like metal or ceramics. That's the reason why student, you are using a lava as some special part in your the systems, I guess. And also, it has a very low modulus. The modulus value is 10 to 5th or 10 to 6 Pascal, let's say like 1 megapascal. And due to the as I already mentioned, that the lava elasticity is coming from the entropic elasticity. It's temperature dependent, and actually, elastic modulus value is proportional to absolute temperature. And I mentioned the Gustav-Joule effect, and finally, more interestingly, the even if you elongate the lava band, then it of course elongated. But as you maybe you can now touch your lava band, then you can elongate it, but maybe the diameter becomes smaller. And as a result, the volume of the stretched lava band doesn't change so much. In using a technical word, its Poisson's ratio is about 0.5. So what? So this compares the elasticity and the Poisson's ratio for the different materials, and metal. It's in a gigapascal level, and some plastics, polystyrene, polyethylene, have also the order of gigapascal level modulus value. But the lava is 1,000 times smaller compared to other plastic materials. And as you can see here, basically upon the stretch, many of the material exhibit the Poisson's ratio of near to 0.3 or 0.4, which means the volume increases. But the case of lava, volume doesn't change. If you don't know what is Poisson's ratio, here is a definition of that. And when we start from this cubic structure and elongate it, and in this way, and then the elongated in one direction and then shrink in other two directions, then the Poisson's ratio is defined as the ratio between this the value and this value. And because now you can now compare the volume change, now that this has the volume of this shape and compare with the cube with the volume of 1, then it has this structure. So if we go 0.5, then delta V doesn't change. So nearly equal to 0. And other sample where the new value is less than 0.5, like 0.3, then delta V has positive value, which means if you stretch the sample, then inside this material, there should exist a void inside this material. But case of lava, void never appear. That's the reason why the volume doesn't change. And what other type of material exhibit this Poisson's ratio of 0.5? Yes, one of the example is actually water. Of course, water cannot stretch in this way or something like that. But if you carefully do some experiment, then we know the water also has the Poisson's ratio of 0.5, which means that they cannot change the shape, volume. So if we have a kind of deformation of the material, because it's liquid-like nature inside the material, then if there is a kind of void, then this void can be compensated by putting some other molecules in it. In this way, the liquid-like material doesn't no. What to say? The void cannot be formed inside such a liquid materials. And there are many different type of deformation this manner. One is uh, what to say? In Japan, in Chinese, you can read it this way. And also kind of share the deformation existing, and also kind of the compression can be also observed, can be made to such materials, and each has the different definition for the modulus values. Uniaxial elongation case, it is called Young's modulus. So the stress and the strain has a proportional relationship, and this proportional coefficient is called as the Young's modulus. And the case of shear, it is called the shear modulus. And the case of this one, it is called the bulk modulus. And these three different modulus has the correlation to each other. For example, the shear modulus can be expressed in this way using a Young's modulus, and by substituting new value, Poisson's ratio of 0.5, then the relations between G and E is 3 times larger, 3 times smaller to each other. More interestingly, bulk modulus is actually can be correlated with the Young's modulus E with this formula. And now, by substituting shown of the 0.5, give the infinite number of dp, and it's impossible. So the 0.5 is not a mathematical value, and experimentally, the lava shows the Poisson's ratio like 0.49 or 499 or something like that. Anyway, due to this portion becomes small, and the bulk modulus is much, much higher than the Young's modulus or shear modulus. These three, the modulus is nicely used in some mechanical component. What is it? And this is so-called seismic isolator, which you can find because you know that the Japan, Taiwan has a lot of earthquakes. You know that then nowadays the many buildings or bridges start to adopt this seismic isolator beneath the building or the bridges. And this was made from lava and metal plate in this way. And then once the earthquake occurs, then the ground moves, but due to this motion is absorbed by this seismic isolator component, the buildings doesn't move so much. And you know, because this is lava, so this movement is easily occurred. And we use not E, but maybe G, the shear modulus is used. So it's easy to move. But please remind that here, on this seismic isolator component, there is a very, very heavy buildings with a, then why lava band doesn't the compressed by these heavy materials. And this is because in this case, we are using this the bulk modulus values. The Young's modulus or shear modulus in the megapascal level, but bulk modulus is already in the plastic or similar to the metal or a, ceramics values. So depending on the direction, lateral direction it's soft, but vertical direction it's very hard. And this is due to coming from the the nature of the rubber material and especially the Poisson's ratio of zero point 0.5, and this 0.5 is due to the rubber is in a liquid situation. In case of polymers in the glassy state or crystalline state, also possible. Like case of the you may also have a pet bottle in your daily life, and that they are actually made from polyethylene terephthalate, and this is in a situation of the semi-crystalline state. So which means the combination in the crystal part and the amorphous part are the no liquid-like situation. So you cannot stretch it. But the lava is in a liquid state, so you can do this way. Now, let's, as a last part of my talk, I also show you an interesting property of lava material. So if I'm your place, then I can bring this one, but I cannot do that. So please look at this movie. So now we have two different lava ball. One is bouncing. Oh, yes. But the other one, this is also has a lava elasticity. But if you raise up it to some height and drop it, then never bounce. The question is, where has all the energy gone for this one? But this is really temperature dependent. If you heat it up, this one, yeah, it start to bounce. Once again, yeah. Once again. So now it start to bounce like in a bouncing ball. This is actually non-bouncing ball at room temperature. And another way to change this property, the property of this non-bouncing ball is cooling down this in using liquid nitrogen. Then yeah, in this case this also bounce, but listen the sound. Yeah, now the sound of the bouncing become totally different in the case of a situation in lava. Actually, this turns into glassy state, solid state, because it was cooled down. So this means that the lava is also become glassy state if it is cooled down. Okay, and these two, bouncing lava and the non-bouncing lava, has a of course they are lava at the room temperature, but so if you push or if you pull, and then it get back to the original shape if the force is released. So these two materials both show the lava elasticity, but upon the impact, like dropping down or something like that, then they show the exhibit the difference in between. One the potassium lava exhibit the bouncing response, and like this isobutadiene isoprene lava is actually non-bouncing the is a non-bouncing rubber. And we know the chemical structure of these, but we don't know why the butadiene rubber show the bounce situation and this isobutadiene isoprene rubber doesn't show it. No one knows. It's interesting. Even chemical structure is very well known. But anyway, what we know is the temperature dependence of each material, and they have a different temperature, transition temperatures. Yeah, as I show you in the movie, even in a rubbery state at room temperature, upon the cooling down, the modulus value increase, and finally it turns into the glassy state with a modulus value 1,000 times higher than the rubber. So it goes turn into the glass, the condition. And here in this situation, the which we call glass rubber transition zone region, the modulus value is in between the gigapascal or megapascal level. More interestingly, if the material is in this situation, energy dissipation occurs. So the non-bouncing ball for first of all, so in case of a bouncing ball, the room temperature is here, around here. So it shows rubbery state. But the case of non-bouncing ball, the room temperature is around here. So it is not. So that's the reason why if you raise temperature up by putting it in hot water, then it turns into this, coming into this region, and cool down its glassy region. And here in this region, energy dissipation occurs. That's the reason why this non-bouncing ball doesn't bounce. And if you are very much interested in such kind of phenomena, then you can learn using this type of model to explain such kind of phenomena. And we call this viscoelasticity. Viscoelasticity is okay. Visco means viscosity. And so this means that the polymer chain, polymer material, it's in it. There are kind of elastic component and viscous component. And this viscous component plays a very important role for such energy dissipation processes. I will not go into the detail because time limitation, and this equation is too much for you, I guess. But just simply show you this simulation result. Now, we have two components, viscous component here and elastic component here. And this is actually the spring with the obeying on the Hooke's law. And this is kind of the liquid medium, and here is some plate in it. So this is kind of so-called so-called dashpot or something like that. You may know that the mechanical component. So anyway, this is a kind of toy model, okay? So, but anyway, this can explain something. So this let us know that if there exist two different elastic and viscous component, then the whole system exhibit the frequency dependent property. Once again, if you move, please imagine that this component, this liquid is very highly viscous. So in order to move this plate in it, you need a very high force. Okay? Then in that case, once again, please have a look. So if you move quickly. Oh, yeah. Then the spring move quite rapidly and following the output signals, but this portion doesn't move so much. So this means that for high frequency, this component are basically acting as elastic material. But the case of a low frequency region, what's gonna happen? You can move this way. No change, no elongation in elastic portion, but you can move this plate inside the high viscous the liquid in this way, and also bringing back to the opposite direction. Then this portion bit shrinks, but keeping this condition and pushing this portion. And as a result, you don't feel so much force from this component. So so this means that you are, in this case, imagine that you are moving your hand inside the water, then you feel a kind of drag force, okay? And similar, the viscous force is now you are detecting in this situation. So this means at the high frequency, this system behaves as a solid and elastic material, and for low frequency, this system behaves like a liquid material. So by changing the input frequency. At the same time, at the center, the middle frequency, both component moves this way. Then, the case of the spring, the energy is stored, and so once force is released, then energy is also released. But the case of this dashpot component, you can, if once you move this the plate in the viscous material, then energy is dissipated and turns into heat. So this viscous component is a key component to understand the energy dissipation occurring inside such kind of viscoelastic material. Okay, so this is the story for the frequency dependence, but the temperature dependence is also same. Then at the low temperature, this viscous component frozen. So the only what to say, only the spring component exhibit the macroscopic properties or something like that. And this is another interesting portion, the difference between the bouncing and the non-bouncing lava. And so please have a look at this movie. Yeah. Bouncing ball go further, and non-bouncing ball stops at some distances. And this actually lava is used in some specialized product. Yes, the bouncing ball is a summer tire, and non-bouncing ball for the winter tire. Especially in Japan, we have a snow. Then we need to drive on icy roads, and then in winter we need to change the tire for the winter tire to the winter tire to make the automobile stop quickly. So we need energy dissipation. So in this way, the different rubber material exhibit different mechanical property, temperature dependent, frequency dependent, and then depending on the original the property, we have a right use of the each material to different purposes. Okay, and this is just a shocking the movie. So if you don't want to look, then please close your eye. But this happened when I was young. This is actually the kind of disaster happened for the space shuttle, the name Challenger. Yeah, I was actually looking at real time when I was kids. And then, oops, sorry. Yeah. This happened. Suddenly, the explosion occurred. Oh my God. Then, after this challenge disaster, some committee was constructed. And actually, the Professor Feynman was the leader of the committee. And he said, because nature cannot be fooled. Why this happened? Once again, because now you know lava can be turned into glass when temperature decrease. But at that moment, NASA guys didn't know that. That's the reason why this challenge disaster happened. So the many lava component was used in this the space shuttle everywhere, especially as a sealing material. But unfortunately, of course, some of the material scientists did know this property change by temperature, but this information was not transferred to the other people. So what I wanted to say is communication between the material scientist and the research and the engineering, like you, have more intimate interaction to each other. That is what I really want to deliver to you during my talk. Okay, lava is just lava in at room temperature, but by changing temperature, it is not true. So once again, please remember the responsibility of the scientists and the engineers to the society. This is actually a message to you. Okay, and the time limitation, I cannot go into the other portion, but maybe it's okay. I have already mentioned about something, but not just a negative message is the last message should not be the negative message. So I first want to show you the some future. Okay, so I was also appearing in another TV program. So this is we are talking about the future tire. Yeah, this is just a CG, but the company Goodyear is really thinking of making this realized. But question is, how you can use this the spherical shape the tire into the automobile is not so easy task, I guess, and the material science only cannot think about it. So maybe also engineering and engineer also need to think about how we can do like this. And also something else is this new material. This is also very interesting material. First, you cut this one, and after that, without adhesive, just push these two each other. Then after 1 minute, now it adhere to each other. So some material scientist is making this new type of material. So this is another reason why the material scientist and the engineer must discuss frequently to have a more better life. Okay, so this is very last slide. So now I think if you are undergraduate or graduate course student, when you are in an undergraduate course student, you have learned chemistry, physics, and mathematics. But in our case, we have learned the material science, especially polymer science, when graduate course student. But not only such science, but also you better to learn social science, and also thinking of the connection with the society, and to make our life better than now. This is a final message to you. Okay, that's the very end of my the lecture for today. And as I mentioned at the beginning, please listen what you felt during my lecture with some short words. That is my home. Okay, that's it. Thank you very much.